Good evening everyone. My name is Prakash and I am from mechanical department. Today I would like to discuss about some few topics about mechanics of solids. So here I would like to discuss about thin cylinders. So what are thin cylinders? So thin cylinders are nothing but the vessels such as some boilers or some compressed air receivers. So these vessels are of cylindrical or some spherical forms. So these are mainly used for storing fluids, the fluids which are under pressure. So here how we say that a cylinder is a thin or thick? So the reason is, if the thickness of the wall of the cylinder is less than 1 by 15th to 1 by 20th part of its diameter, so these cylinders are called as thin cylinders. Or if the thickness of the wall of the cylinder is greater than 1 by 15th to 1 by 20th part of its diameter, is called as thick cylinders. So here, in case of considering some thick cylinders, so we have to assume that the stress distribution is uniform over the thickness of the wall. So here I am considering one cylinder. In the cylinder I placed a fluid which is under pressure. So here I am considering some cylinder. In the front view the cylinder looks like a rectangle like this. In the side view the cylinder looks like a circle. So here I am considering the diameter of the cylinder is D, thickness of the cylinder is T, and P is equal to internal pressure, that is fluid pressure acting on the walls of the cylinder, and L I am considering as length. So these are the terms I am considering for this cylinder. So due to the internal pressure in the cylinder may fail by splitting up in two ways. Those are, so in these two ways the cylinder may fail by splitting up in these two ways shown in these figures. So here the forces which are acting vertically upward and downwards on thin cylinder, these forces tends to burst this cylinder shown in this figure. So here these forces are splitting the cylinder. So and also the forces due to the pressure of the fluid which are acting at the ends of the thin cylinder, these forces tends to burst this thin cylinder like this. So due to these two forces, one is acting along the circumference of the cylinder and another is acting at the ends of the cylinder. So based on these two forces, two stresses are developed in the thin cylinder. So those stresses are circumferential stress, which is also called as hoop stress, which is indicated by sigma 1. And the second stress is longitudinal stress. So the longitudinal stress is indicated as sigma 2. So here the names of these stresses are given according to the direction of the forces direction in which the stresses are acting. That means the stress acting along the circumference of the cylinder is called as circumferential stress, or the stress which is acting along the length of the cylinder is known as, that is in the horizontal, that is longitudinal direction, is known as longitudinal stress. So and also we know that circumferential stress is also called as hoop stress. So now here we would like to find out the expression for hoop stress. So as we already know, we are considering one thin cylinder which is subjected to an internal fluid pressure. So here the circumferential stress will be set up in the material along with longitudinal stress. So if the bursting force or if the force inside the cylinder due to this fluid is breaking the cylinder in this way, in this manner, so there will be development of circumferential stress along the walls of the cylinder. So this bursting will take place if the force due to the fluid pressure is more than the resisting force, which is due to the circumferential stress set up in the material. So in equilibrium condition, these two forces are equal. So by obtaining this expression for hoop stress, we have to find out the forces which is due to the pressure of the fluid and the force or resisting force which is due to the circumferential stress. So by equating these two forces, we can get the formula for hoop stress. So initially I am considering the pressure inside the cylinder is P. P is nothing but pressure inside the cylinder, and D is internal dia of the cylinder, and T is the thickness of the cylinder, and sigma 1 is the circumferential stress or hoop stress. So now I am calculating the force due to fluid pressure. As we already know, the formula for pressure is force by area. So now we want force, that means pressure into area. So here we can write pressure into area. Here area is nothing but on which the pressure is acting. That means P into, here the pressure is acting at the diameter D and across the length L. So here the area is D into L. So area is D into L. So that means P into D into L. And now we can calculate force due to circumferential stress. So as we know, the formula for stress is resistance force per unit area. Here we want that force, that is stress into area. So here stress is nothing but sigma 1 we are considering, and area is nothing but area on which this sigma 1 is acting. So here sigma 1 into, on which area the sigma 1 is acting? The sigma 1 is acting along the thickness and along the length. It is acting on the thickness of the wall and along the length. So here the area is L into T on one wall and L into T on another wall. So here the area is L into T plus L into T. So it can be written as sigma 1 into 2LT. So on equilibrium condition, these two forces are equal. That means equating these two equations 1 and 2. So here we can get P into D into L is equal to 2 sigma 1 into L into T. For sigma 1 we can calculate PdL by 2LT. Here L cancel and sigma 1 is equal to PD by 2T. So this is the expression for circumferential or hoop stress. So now we have to find the expression for longitudinal stress. So if the bursting force of the cylinder takes place along this section, that means like this in this figure, here the bursting force of the cylinder acts as ends and the bursting will take place along the length. So in that time the longitudinal stress will be developed in the material. So now we have to find that longitudinal stress. So here also I am considering, as we already know, P is internal pressure and di is equal to internal diameter and T is equal to thickness and sigma 2 is equal to longitudinal stress, as we are considering in the starting of the derivation. So longitudinal stress. So like calculating the hoop stress, we are also following the same procedure. Here the force due to fluid pressure is calculated, and after that the force developed due to longitudinal stress is calculated. In the equilibrium conditions, the cylinder does not break and these two forces are equal. So by equating these two forces, we can get the expression for longitudinal stress. So initially we have to find the force due to fluid pressure. Here the force due to fluid pressure is P into area on which that P is acting. Here pressure means P. Here area is nothing but here the force is acting at along the circle, that means along the diameter, that means it is acting at the circumference of the cylinder. That means here we can take the area as the circle area. That means here the area is pi by 4 d square. So after that we find the resisting force due to longitudinal stress. Resisting force due to longitudinal stress. That is, what is the formula? Here the force due to longitudinal stress is sigma 2, as we are considered, into area on which this sigma 2 is acting. Here the sigma 2 is acting at the circle of the cylinder. That means this is the side view of the cylinder I am drawing for understanding purpose. So here the stress is developed in this place. That means simply the stress is developed opposite to that force. Here the stress is developing. So here the stress is developed at the circumference of the circle, circumference of the thickness. That means here the area is taken as, the circumference of the circle is taken as pi d, and it is acting at the thickness of the cylinder. That means pi d into T. So in equilibrium conditions these two forces are equal. So by equating these two forces we can get P into pi by 4 d square is equal to sigma 2 into pi d into T. We want sigma 2. That means P d square by pi d T into pi by 4. Here pi cancel and d one time cancel. we can get sigma 2 is equal to PD by 4T. So this is the expression for longitudinal stress. So this means this clearly shows that longitudinal stress is equal to half of circumferential stress, because here the sigma 1 is pi d by 2t and here the sigma 2 is pd by 4t. So the relation between hoop stress and longitudinal stress is half of circumferential stress. So friends, I think it will understand. Thank you. We will meet for another class.